All right. Making sure everything is working. Cool. Cool. All right. Let's begin. Storage scalability. Again, I'm going to cover one chapter at a time till the end of the semester, and we should end up with at least 2 weeks for you to catch up if you've fallen behind anywhere. This week's chapter will be all about storage scalability. And as always, if you run into any questions, feel free to put them in the chat because I have all the chats up. The first part, or I would say like the first half of these lessons, you can do generally within your current infrastructure. The lessons 4, 5, and 6 kind of start going into the big data centers. So part of this, I feel you could easily apply to an infrastructure that you create to test, to practice with. And then the others, you're going to need a much bigger setup in order to play with. Some of this will be review as it builds on from the stuff that we've discussed earlier. For example, VMFS, the high performance cluster file system created by VMware for their infrastructure. 5 and 6, with 6 being the most current version of these data centers or these data stores. We know that their maximum size for a single extended 64 terabytes. A virtual disk can be hot extended up to 62 terabytes. The block file size can be 1 megabyte. Obviously, version 6 has some settings that don't exist in version 5. For example, in the latest, we can do things like having up to 4,000 paths. We can have up to 1,024 data stores per host, whereas we can't do that much in earlier editions. With 6, you have all the capabilities of 5, including faster file creations, parallel disk operations, and much more. Here is an area where the two divide. With 6, we can handle these new drives, these 4KN drives that can handle a lot more data and have more capacity. VMFS 5 cannot handle these 4K. 6 can, but 6 will show them to VMware as 512Es. Nonetheless, if we're talking about high density storage, you're going to want to go with the latest edition of the MFS. There are some limitations. For example, only the local SAS and SATA drives are supported. Anything that's SSD and VMEs are not supported yet. Booting is possible as long as they're UEFI. And multipathing should be done within VMware, not outside, using a third party. Delta disks, when you create snapshots, depending on the format, 5 or 6, it's going to be a little different between the two. For example, the SE sparse file, the space efficient, is used by 6, not used by 5. And it's the default in 6. So it's going to be more efficient with your storage. Now you can't just upgrade from 5 to 6, you actually have to create a new data store. So if you are walking into an infrastructure that has VMF5 installed, and you suggest through your consultation that they should install 6, well, what you really should do is migrate. You should use vMotion to move everything that they have in 5 over to 6, and then reformat that VMS5 into VMS6. But there is no clean way to take the 5 and just upgrade to 6. If you're watching this recording, here's a question for you. Select all that apply. What scalability and performance features are available only with VMFS 6? Your answers are those 3. Because this is specifically a VMFS 6. Item number 2, the storage API. This helps storage vendors appear uniform to VMware, which is great because you don't want to have more code in between your virtual machine actions and the physical hardware. You want to keep it as clean as possible. One of the advantages of these APIs is it'll offload some of the work off of the CPUs and into the physical devices, which means less processing time and more things are done quicker, which is essential when we're talking about services that are critical to our infrastructure over large data centers. This is good to be able to offload some of that work over to other systems to do. As long as the NAS system can support hardware acceleration, it is possible to take advantage of that. Again, reducing the overhead on the CPUs and moving that over to the NAS files themselves. Thin provision, which we have talked about in the sense of the virtual machine disk file. So interestingly enough, when you have file size reductions or you delete, they don't actually delete on the LUN. So that space is still there, because these layers that you see here, just because you delete at one layer doesn't automatically translate into free spaces at other levels. So just because there's free space in the guest OS doesn't mean automatically that there's free space in the VMDK, in the file system, in the LUN, in the storage array. It doesn't translate down. In the traditional sense, if you deleted these 3 VMDKs, that free space is not necessarily free. Your LUN will still think it's occupied until you do a command like the SCSI unmap command. Then it will mark that space as free in the LUN to be used. Well, VMFS 6 actually does this for you by default. VMS 5 does not automatically reclaim space. Another reason to upgrade to 6 from 5. And that's, of course, if your hardware is able to do it, because there are hardware that is unable to run the latest version of VMware products. But just so you know the difference between 5 and 6. If you have VMFS 5, you know that anything you delete won't automatically take effect on the actual LUN itself. You have to do a command in order to get that free space back. Because VMFS 5 doesn't do this automatic, you're going to have to run some commands yourself. You could automate this as well with Power CLI. But again, ideally, you would want to use VMFS 6, who did this already for you. In 6, you can define the priority to reclaim space and how much space to reclaim in unit sizes. You can also set a fixed unmapped rate, the rate at which this automatic process happens. Does it happen at 100 megabits a second? Does it happen up to 2,000 megabits a second? You can define that. Of course, this depends on your storage array's capability. So you don't want to tell it to do it at 2 gigabits if your system doesn't handle 2 gigabits. That's going to cause some problems. So 5 and 6 can do it. One is automatic, one is manual. Some guest operating systems, like the Windows Server, is able to send that unmap command straight to the array. So some OSs can do it. Some of your guests, not all of them. You can configure a specific VM to be able to do this. Again, for 5, it's only a limited number of guest OSs. They have to be thin provisioned. The guest OS has to be able to identify the disk as thin provisioned. You have to have hardware version 11 or greater. And the enable block delete has to be set to 1. So again, with 5, you're going to have to do a bit of work. With 6, it's already set, so it ignores the enable block delete. Here's another question for you if you're watching the recording. In what ways can ESXi hosts benefit from using storage devices that support vSphere Storage API? Select all that apply. And the answer is those 3. Storage awareness. Connecting your storage arrays to vCenter. Developing a software component called the storage provider. That'll be the way to communicate. Your storage providers have a couple of benefits to your environment, such as it'll be aware of the topology that it's in. It'll be able to monitor health for you and configure VMs to use the correct storage. DRS can use this information when handling where VMs go and migration decisions if you have this enabled. Part of making this whole data center autonomous, really. This whole thing has been evolving, currently in its 3rd version. In general, the storage providers will give information to vCenter that vCenter can then use to make decisions or to give you alerts, or both. Which is great because you don't have to go to each individual system to see how they're doing. You can just check it from one place, vCenter. So if you have the storage provider, you would configure it. The vSphere API for input-output filtering is another framework that can intercept and modify the input-output within VM kernel before it goes to the physical storage itself. There are third-party vendors that have worked with VMware to provide these filters. The big four filters are replication, encryption, caching, and storage input-output control. So again, this framework intercepts the input-output before it reaches the physical box or the physical drives in whatever format they are, whether it's VMFS, NFS, VSAN, or virtual volumes. This is the order. Replication will be first, encryption will be second, third will be caching, and four is storage input-output control. You can install several filters from the same category on the host, but you can only have one filter from the same category per virtual disk. So it's limited by the disk, not so much managed by the VMs. Your pre-installed filters are VM encryption and storage input-output control. Your third-party filters can be added with with whatever vendor you have's instructions. And any of those providers, after installing it and registering it, will provide those capabilities up to vCenter to be used. Then you can make policies, which we'll talk about. You can see within storage provider, you'll be able to see what filters exist, and they'll be added to each host. So here's a quick question of what is the order? And the answer is that. I mentioned policies, and now we move on to policies. Your policies help you ensure that virtual machines can use storage and guarantee a certain level of capacity or performance or availability. This is where we start to make storage into something abstract, kind of like VSAN or the virtual volumes. This is where we're applying a universal framework, irregardless of what is actually running our storage. So we're starting to get away from the physical, we have 6 hard drives and 2 solid states, starting to get away from that specific sense and starting to become more abstract. And as we continue on through these next sections, you'll see we get more and more abstract because we're looking at things at a macro level instead of at a micro level. So with policies, we can do things like advertising storage capabilities, like the input-output filters that we just talked about, the bidirectional communication between the hosts and vCenter, and virtual machine provisioning based on the policies. These policies will be essential to virtual machine provisioning. Now, it'll choose what type of storage will be provided to the VM, where or how it's going to be placed within storage. You'll see this more as we move further. The policies are made by rules that you can define, and there's quite a list that you can use to define these rules. You said they're your basic element of the policy. So it could be capacity-based, it could be tag-based, or data service. something like RAID or what tier or caching or replication. For example, we can make a gold policy for a specific application. That means that application will only use the solid state drive. So it will be faster to communicate. Whereas the operating system may be set on the silver policy. So it'll go on a hard drive. It'll be a little slower. Because we want the application to work faster, but the operating system, it's not that top priority. You can do this kind of crazy stuff with these policies. Again, your services will depend on your storage provider, whatever you have, but they generally fall into the four that we talked about: replication, encryption, caching, and storage input-output control. All depends on what you have. Here is an example of a storage policy. We have the high performance, the standard, and the basic. And we have some components that we want to use. We have replication happening in 2 hours for our high and standard, but our basic can replicate every 4 hours. We're fine with the changes that happen and save or replicate every 4 hours. It's not as important as the other two. Here's a quick question. Data service rules are used to help storage policy-based management place VMs in the proper storage. The answer is false. It's capacity-based and tag-based rules that'll guide decisions on VM placement, not the data service rules. The whole process is about 5 steps. It might vary a little bit depending on your setup. So number one, you'll need to configure the storage that'll be used in the policy. You'll create tags if necessary, but typically you'll use things like VSAN, the virtual volumes, and the input-output filters. Then you'll create the policy component. That way they can be used within a storage policy. Some are built in already, but you can create your own as well. You'll have to specify the storage type, and normally it'll be VSAN or the virtual volume, or virtual volume with traditional storage. In this example, a storage policy was named the silver tier. And we're going to use traditional storage or VMFS. I'm going to put specific rules, and it'll be tagged. So they add the silver tag to this. Then it shows us what storage do we have, what data stores fit this new tag and new policy that we're making. We'll apply it. We'll say, yes, this one who is compatible will now apply. So this data store will now get this policy to it. And then we can check compliance to see which VMs are compliant with this policy. And you'll have a lab to do that. We have reached the halfway point. And like I said, we're going to move our way, becoming more abstract as we go through lessons 4, 5, and 6. This will cover VSAN, which we have talked about before, that the storage solution made by VMware where you can use solid state drives as cache and use more solid states as capacity, or use hard drives as capacity. You can use it as all flash or hybrid. If you go all flash, if you have the budget to go all flash, you could do the deduplication and compression along with RAIDs. Disks up to 64, from up to 64 hosts, can be grouped to form a VSAN data store, each host containing 5 disk groups each. So we can have a total of 320 disks, physical disks, into a VSAN. That's 5 disk groups. And a disk group could contain 1 cache device and up to 7 capacity. So really, we're looking at 2,560 disks in total that could be used in a VSAN. That's crazy. That's a lot of disks. A VSAN will store and manage the data for you by turning all the data containers into objects, because they'll essentially flow between these hosts now. Everything will be an object. Again, turning things more abstract. VSAN will show up as a storage provider. And through that, you can add, you can see the capabilities, the data services, and all that kind of stuff, along with defining any storage policies. You can have multiple virtual machine storage policies in a single VSAN storage. There is a default already, and you can make more to apply. To make one, it's a simple wizard. You define the storage type. You define a couple rules, like the availability and the site disaster tolerance, or the number of failures that we will tolerate. And you see the list right here. You also have the advanced policy rules and the tags that would go with this. Further on, we have the virtual volumes, the abstract containers that replace traditional storage volumes based on LUNs and NFS shares. These could be fiber over Ethernet, iSCSI, NFS, or fiber. The virtual and physical components are able to interact with one another and provide that virtual volume functionality. Again, getting more abstract. The virtual volume provider is actually a software component that is the mediator between vSphere on one side and the storage system on the other. At this point, we are forgetting the array exists and all. It's now a storage container. It's a virtual volume. There's a protocol endpoint that exists that can help be configured on the storage system side. Each volume is bound to a specific endpoint. And a single protocol endpoint can connect many virtual volumes together. Again, your virtual volumes will be grouped into storage containers. Each container has an underlying hardware and logical groups that we are no longer really focused on at this level, at this macro level. So you could have storage containers for particular organizations. You just use the virtual volumes to map to a specific storage container from there. The objects that are stored within these will be connected through Ethernet or fiber, some high-speed network. These virtual volumes are not pre-provisioned, but they're created automatically when you do virtual management operations. Now, so like I said, at this level, we don't care anymore how many drives are in and the arrays. We just see these storage arrays and these containers as just an abstract thing where we have a virtual machine and we know that within there exists the configuration files, the VMDKs, any snapshots, and they're connected directly into virtual volumes. But it is much more abstract at this level. We know those things exist. They're just we just don't know exactly where they are anymore because it could be anywhere. Virtual volumes are able to replicate as long as the software is pretty much up to date and they're equal to each other. They'll be able to replicate. Any virtual machine running on a virtual volume does require the storage policy. If you don't create one yourself, there is one already that exists. And the storage array would basically be in charge of determining the optimum placement for virtual machine objects. So you're letting the system decide by default unless you configure it. As with any policy, you could have multiple so that you affect at a granular level, like these three examples. A virtual volume containing a data disk that has a richer set of services than the virtual volume for the boot disk, a snapshot virtual volume that has different storage tier compared to the data, and replication. Because maybe one virtual volume that you have has nothing but SSDs, and another one has hybrids, and another one is just a bunch of hard disk drives. You can define your rules to break apart a virtual machine into those pieces to fit the different architectures. Creating these policies is just like all the others. You define the name, a description, the data store specific rule. And you can see those rules and make some edits as needed. Here's another quick question. If the capabilities of your virtual volume storage array do not appear in the policy, what should you check? And the answer is the third. Make sure that it's registered with vCenter, because that's where everything is looking. Have another lab. Oops. Number 5, the storage input-output control that we've talked about earlier. Now we'll dive a little further in. Storage input-output control prioritizes workload to the physical disks. For example, you could have these 6 VMs, and they could all be equally using the system, equally accessing the storage. But with it on, you could prioritize things like your online store and your mail server to take, to be priority over these guys. So if the data mining and the print server need to access the data, but these guys need access to data, they'll go first, then these guys. Ensuring that the most important VMs get adequate resources, even in times of congestion. That's where this really comes into play. It is disabled by default, so you'll need to turn it on. And you'll need to define the shares, the upper limit of input-output operations per second, and the reserved input-output operations per second for virtual machines. You can also have it monitor latency and throttle based on that. By default, this whole control system uses an injector-based model to detect the threshold. You could do it yourself. By itself, it would look at the latency. It would see in this example that, we see the peak, so we're going to set the threshold to 90% of that value. Again, it could be done automatic, or you could do it yourself. You can implement it as an input-output filter, just like all the others. Here is the creating that policy for storage IO. And you could be specific or use any other storage policy component. Some requirements. Of course, the data store has to be managed by a single vCenter system. It supports fiber, iSCSI, and NFS. It doesn't support data stores with multiple extents. And if you're using something that's backed by arrays, then that array should be certified by VMware to be able to do this. You can't just apply it and think that it'll work on any system. So here's another quick question. On a data store with storage IO control enabled, to list the steps that you would perform to ensure that the online store VM and the mail server VM have higher IOPS than the others during point of contention. So you would create a storage policy that uses the predefined storage policy component called the high IO shares allocation. So it already exists. That has a disk share value of 2000. So you would assign the storage policy only to the online and the mail server VM. Everybody else would get the 1000 disk shares. That would make those two priority. The last lesson is the Datastore Clusters and DRS, subjects that we've covered before, but now we're looking at from the point of optimization. A Datastore cluster is just a collection of data stores that don't function together, whereas the one enabled for storage DRS do work together. Of course, you can't just turn it on. There's going to be some guidelines in order to be able to do this. Like all the data stores in the cluster have to be the same format. The VSAN and virtual volumes are not supported in the data store cluster. Data store shares across multiple data centers can't be included. and you don't want to include hardware that is hardware accelerated and isn't hardware accelerated. You want to keep it one or the other. This can be set up as a one-to-one, one-to-many, or many-to-many, depending on your setup. A quick review of DRS, allowing you to manage aggregated resources of a data store cluster. When a VM is created, DRS will look at where it can go, along with when VMs are cloned or migrated. DRS will select the member data store based on the capacity and on IOPS load and move them as needed. The 3 affinity rules that help determine that are the intra VMDK affinity, which means the virtual machine files and the virtual machine disk files are on the same data store. The anti-affinity keeps the virtual machine VMDK on different data stores from the VM. The anti-affinity rule, so that the VMDK anti-affinity separates the disks. The VM anti-affinity rule separates the VM itself, the VM configuration file. So in the first, we have everything together. In the second, we split up the disks between different data stores. And in the third, we separate the virtual machine configuration files across different data stores. Again, it all depends on what you have that you can apply these different rules and the level of criticality for the VM that we're talking about. Because if we're talking about a VM that hosts information, you probably want to ensure that that information is replicated everywhere. Or if it's a high critical system, you probably want to split it up so that if one data store goes down, another can pick up the VM and continue. vCenter will, of course, give you recommendations for DRS. Any migration recommendations usually occur when input-output latency is exceeded or space is exceeded. A data correlation refers to the data stores that are created on the same physical set of spindles. It'll detect it based on individual data store performance or the combined data store performance. This is enabled by default. Of course, it is customizable. So you are able to get within your data store cluster and you're enabling DRS, you can set some specific items. When storage DRS has to go into maintenance mode, it'll move VMs out of the way so that you can do whatever work you need. There are options to back up virtual machines that, of course, will add latency to a data store, but you can schedule when to do that. So you would ideally do it in off hours when no one will really feel that effect. So here's another question. We have a data store cluster, and this VM, or these two, handle DNS, which is a critical service for our network. Which of the rules that we talked about earlier would prevent the single point of failure? And the answer is a VM anti-affinity rule. It'll ensure that the VMs listed in the rule are always placed on different data stores. So if a data store fails, the VM itself will continue. And we won't lose DNS. The default migration recommendations are listed here. And what vSphere technologies are supported. Storage DRS works with the Site Recovery Manager. You will see some loss during maintenance mode, but that's okay. When we have replication on, those replica disks are created at our secondary site, determining the space usage, and the disk will be balanced at our primary and secondary sites. If you have virtual machines that have storage policies that are living in storage DRS systems, you can enable those policies or force it to not violate certain storage policies, again, depending on the VM and what it's going to be running. Another chart showing you storage DRS and the features with storage arrays. A lot of this can be automated for you, so you don't even have to worry about it. There is also deduplication awareness. Whether one or more data centers have a common storage pool to avoid moving virtual machines between data stores that are not in the same pool. There's also storage awareness for the thin provisioned. For example, avoiding migrating virtual machines between two thin provisioned data stores backed by the same pool. You'd want to copy into a different pool. Our vendors are offering auto-tiering arrays. And of course, these vendors don't necessarily work together. They all have their different setups. So you'll have to work with your vendors to figure out the appropriate performance modeling for whatever vendor product you have. DRS and storage input-output controls are complementary solutions. Storage I/O working in real time. Storage DRS does not use real time, but they can work together. And you have another lab to do. Cool. With that, we have covered all of chapter 3.